for the reminder once again. And I'm going to jump over to the notes that none of you guys could see. Switch the screens, and all right, we're in action. So last class, we covered linear models. We talked about how we estimate a linear model, and we also talked about interpreting beta and standard errors. And we also talked about R squared as well, right? And so, I spent a lot of the class, and hopefully, this being one of the bigger takeaways that you take from this class is the value that we place on those particular items, right? Betas, standard errors, R squared, as a discussion about what constitutes a good model, okay, which these things do not tell you necessarily. We really want to focus on what those things actually mean, right? And so, I kind of alluded to, well, there's other things that we ought to consider as well. And so we're going to continue thinking about some diagnostic tools that you can leverage when you're running a linear regression, which is not to say that we should exclude these guys, right? So we still want to think about these in the context of what they actually contribute to our interpretation of a model. But today, we're going to think about other ways to think about how do we tell if a model is good. Okay? So we're going to talk about residuals, RSE, we're going to talk about MSE today. Okay, so right off the bat, let's start by talking about residuals. So this is the deviation between observed value and estimated value. So we have been kind of using this interchangeably, calling it the error term, right, in the previous lectures. And so if I were to explicitly graphically show you what the residuals are, they would be like this. So X and Y. Okay, let's see. I'm going to do A, B, C. So I have points of reference here. Okay, and so if I have a line that I fit through all these guys that looks something like this, okay, the residual is referring, right, to the distance between my predicted model and the true values or the observed values. So my observed values and estimated values. So that is referring to the distance from the line to each of my data points, okay? Okay, and if that is, let's say this is, okay, this is not to scale because I'm terrible at replicating this from my notes, but let's just say the distance is 2. Let's say this is 2.5. Let's say this is 1. Let's say this is negative 2.5. And this is negative 3. Okay? So I can actually look at the residuals themselves. Okay? And so if I plot my residuals against My y hat. So I have A, B, C. And then let's do something like 0, 1, 2, 3, -1, -2, -3. Okay, so on A, I have 2 points, one at -2.5 and one at -3. So A, there's a point here, and there's another point here, right? So this is at -2.5, this is at -3. Okay, at B, I have a point here at 2, so I can just plot that. So I have a point here. And then at C, I have points at 2.5 and 1. So this is like this, and then 2.5, all the way out here to C here, and then I have something out here at 1. Okay? And so this is residual on the y-axis. Yes?
Is there any difference between error and residual?
No. It's the same thing, yes. Okay, so I'm plotting my errors or residuals. Yeah, so, okay, let me caveat that, which is to say that we've been using residuals and errors interchangeably, and nothing that I've said I don't think is incorrect. But I think I'm going to start to switch and just call them residuals at this point, because there are other things that an error can refer to that we'll actually talk about in a couple lectures. So just to be a little bit more precise, I'm going to just start calling them residuals. Okay. Me calling them errors at the beginning, I think that's a little bit more easy to associate. But from here on out, I'm going to do my best to try and call them residuals. I may slip in an error here and there. But to be more precise, because we're going to refer to other aspects of like a statistical error, we're going to try and be robust and call them residuals. Okay? Any other questions about this? So this setup is just so that you guys can understand what a residual is and kind of visualize what they kind of look like. You can actually plot them out explicitly. And so, right, so residual is equal to observed minus predicted. Okay, and so why do we even bother doing this, or why do we care about the errors? So it actually turns out that this is a very powerful diagnostic tool when it comes to thinking about regressions. And so what I want to do now is show some examples of residual plots, and then we're going to think together about what they mean. Okay, so here's the first example.
Hey, Alan.
Yes.
Question about the residual plot.
Yes.
Say if you go to so y hat, that's predicted value, right?
Yes.
So if we go to y equals a on the plot on the left,
Okay.
why does a line up with observed values and not predicted values? Should it rightly line up with about where the red line crosses the y-axis? Because looks like where that line is going.
Yes, actually, you were right. Yeah, I accidentally,
I guess we plotted residuals for yi.
yes, which is incorrect. Good catch. None of you, see, I was testing you guys, and none of you guys caught it, except for Christopher. Yeah. Um, it's funny. I was like looking at this, and I was thinking that this residual plot should maybe look a little bit different, for reasons we'll get into in just a second. And actually, it's the reasoning for it is actually I've made a mistake. We should be plotting against the points that correspond to where you intercept. So here, that's exactly right.
We can't see where you're drawing.
Oh,
There you are, sorry.
so yeah. So I'm marking out these points. So we should be looking at those points instead of these points. Yes. So yeah, let's just do that. Okay, so yeah, that's very good catch. Because actually one of the things that I was gonna say is that you always want to be plotting against y hat and not y, precisely because you actually get a skewed residual plot, which is what I'm showing here as an example on purpose. Okay, so let's redo this, and we're gonna have to draw a couple more points here, and I'm gonna call these as A, B, C, D, and E. Okay. So now we have A, B, C, D, E. And okay, so A is 2, B is negative 2.5, C is 2.5, D was negative 3, and E was 1. Okay, so this actually looks way better. And let me talk about why I say it looks better in our next examples. Okay, but this now looks like what I thought it should have looked like. These are the same notes that I used last year, which means no one last year caught it either. So good job. Very, very good catch. Means we are actively thinking about the notes as you take them. Very good. Okay. So there's something about like the blue dots that I put up versus the green dots that I put up that like I am now intuitively like, oh, it's a relief because I see something happening there that makes more sense to me. And so I wanna build up that intuition for you guys as well. Okay. So this is a hypothetical plot of residuals. And so I want to ask you guys, let's go backwards from the residual plot to potentially what this might look like in the model fit versus observed values. Yeah.
Was thinking out is that no residuals on the negative side, so you're always under-predicting the actual.
So the residuals are all on the positive side. They're all above 0.
Oh.
Yeah. But yes, that.
Yeah. Oh yeah, so you're over-predicting.
Yeah.
Yes.
No, I think you're right.
I meant, oh, I see what you're saying. I meant to say that the residuals are positive, but you were saying that the,
Yeah, the
yeah,
results
yeah.
are, so you're always under predicting, right?
Oh, okay,
The
so I
model
meant,
is always lower than the observed value.
it's observed minus, so I made another mistake, which is then that this observed minus predicted, so these are positive and these are negative. I mean, like practically it doesn't matter, right?
Right. So it's predicted minus observed.
No. Oh my God. No, it was right. You're right. You're right. It was right. Okay, I made one mistake. I didn't make two mistakes. Okay. I am like massively flustered right now because I'm mixing up underpredict versus overpredict. But the point is that all the residuals are on one side of the zero, right? What does that mean, right? That means that in our prediction, observe minus, they're all going to be, all of the points are going to be located above the line, right? Does that make sense to everyone? Because we're above zero, so therefore all of our residuals are positive. And so anything that's under would be negative, right? And so you don't observe that happening. And so here, since they're all positive, our model fit, our prediction against the observed ones is like very clearly biased, right? Remember the whole thing, the very first example that we had, right? We intuitively say that the fit looks wrong because it's like farther away from all the points. It's not going through the points, right?
Is that going to happen? Like, if it's trying to minimize the square?
So it shouldn't happen, right? But the point that I'm making is that even if you weren't able to observe this, okay, and you were able to observe this thing, just from the residual plot, I can say something about how the model is performing. I can say that, in this case, I will say that the model is biased because the residuals are not centered around the zero, and it's saying all the errors are positive. There's like alarm bells that are ringing here. And so residual plots as a diagnostic tool is actually very powerful, and that anytime you guys are doing regression, you really should be doing this, okay? And yet, has anyone ever, in any peer-reviewed publication where they publish coefficients and standard errors and R-squareds, has anyone ever seen someone plot a residual plot? Yeah, but you know, this is a very powerful indicator for bias, right? Yeah.
I want to know if there's any like coefficients or something like the least square method to show this, or the only way to show this is via like the drawing a graph of this.
Yes, but the graphical nature of this is a very good feature. You can, via very simple rules, I can make a lot of diagnostic inferences about what's happening in the model just by looking at a very simple plot. And, you know, I was referencing the fact that you don't have access to this, right? And so you guys might be thinking, well, why can't I just plot this thing and look at this as opposed to the residuals? And the answer is, does anyone know why you might not be able to do that?
I guess in the residual plot, you're kind of normalizing the y-axis versus the predicted values. I guess like if you were to like rotate the whole graph on the right so that the line was horizontal, sort of transform everything in, so that the predicted line is a flat.
Yeah, actually, that's a way that people have visualized that before, but that's not what I'm getting at, because you could do that, right? Yeah.
Because we usually have like multiple linear regression where you have like
Yeah.
multiple dimensions stacked
Yeah,
up.
okay, so this is x versus y. What if you have two variables? Now I have to look at a plane that goes through a cloud of points in 3D, right? And so, okay, I can visualize that. I can still do that. Okay, what if we have three variables? Oh shit, I can't do that anymore, right? I can no longer visualize this relationship across everything as soon as I'm in 3, 4, 5 variable range. You could conceivably do three variables with like a color and like a gradient or something. But yeah, good luck with that. With residuals, I can do that in any dimensions, right? It's all just y hat versus residuals. So this tool can be applied to, really any regression. And in fact, you could do this in nonlinear regressions as well, right? That it would work perfectly fine. So, this is a very robust way of soliciting bias in the model. Okay. Let's look at another example. What would the counterpart to something like this look like? Okay. Dum, 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 dum. So in the first example, we saw that the points were not centered around 0, and that intuitively tells us something about the errors being biased in a particular direction. Here, the errors are centered around 0, but they're in this kind of pattern. So let's think about sort of generically, if I were to go in the reverse again, what would that plot look like? Yeah.
The observed values are probably like in the form of like an inelastic curve.
What does that mean?
Like a curve that's like flattens over time.
Possibly, but big negative, small positive, big positive, large positive, and then back the other way, right?
I guess it tells you for low and high predicted values, your residuals are negative here.
Let me draw it, and we'll see. Okay, so if I have a line like this, the first error was really negative. The next error was smaller negative. The next error was slightly positive, and then really positive, smaller positive, kind of negative, bigger, and like this. Okay? So, generally speaking, when you observe non-random patterns in the residuals, this actually tends to mean your fit, it's not a good fit for kind of a plethora of reasons, right? The line, the parametric assumption of linearity in this particular case is probably not a good one. And oftentimes that's what patterns in the residuals, non-random patterns in the residuals can tell you. Okay? So across these two examples, we're showing the kind of two pieces that you want to latch onto when you are diagnosing a model through residuals, which is non-random patterns of residuals and being centered around 0. And if you are running into either or both of those things, then your model is probably biased in some way, and you probably want to look into doing certain things to improve that. Okay, and so just purely as a diagnostic tool, right? That's a pretty easy way of being able to tell these things. Okay. Any questions about that? Yes.
Can you actually infer what the model looks like just from the residual plot?
No. But I was making, hypothetical example. But you generally can't really do this because this actually doesn't. There's no information contained here that really tells you anything about the characteristics of the actual fit. But just for the illustrative purposes of like what these residuals mean and how to interpret them, I'm doing this like hypothetical thing where we can move backwards. Yeah. Okay, any other questions? Okay, so let's jump over to R. Okay, we're gonna use, just to show the residual stuff, we're gonna use the same example from before. This might be taking a larger sampling of points, I don't remember, but here we are building that same hypothetical function. And then oh no, what did I do? Oh no, that's right. No, that's not right. What the hell happened?
Did you auto something like that?
There might have been some kind of autocomplete thing happening. Okay. Oh, there's a missing period there. Okay. Not having like visual feedback of what I'm typing is like surprisingly difficult. Okay, so this should look familiar to most of you guys. So run my X, run error, run the Y, put it into a data frame, run the regression, and run the summary of the regression. Yeah, and this looks, oh, you know what? This is a little bit different. I've made the error a little bit larger in this example, but okay, but that's okay. That's not going to affect anything.
Yeah, I guess you make the standard deviation 50.
Oh, did I make it 50? It should be 5. Sorry. Let me do this. Okay. Try again. I should make this a little bit better. Yeah, okay. I was like, it seems really different. Okay, yeah. Let's take a look at the data frame for model 1. So I have a column of x's and I have a column of y's. These correspond to, right, if I were to plot x comma y, these points correspond to points in here, right? And then I have a line that fits through all this, so AB line, what's it called? Example.model1, comma, color equals red. Okay, and then, that's our model. So I want to be, extra clear here in terms of how we actually go about calculating the residuals. Okay, and so who can actually help me understand how to do that in English, not in code? How do I calculate my residuals? Yes.
Plug the x value into your regression equation you got from your model results.
Okay.
And
And what would that give you?
the predicted y.
Yep, that's right. And then,
And then do the observed y minus the predicted y.
perfect, great. Okay, and so how do we go about doing that? So let's see. There's actually a couple ways that I can. So essentially, what was described is we want to generate a column called y hat, which is the predicted value corresponding to each point, right? And so for this point right here, I want to figure out, given this x, where is it on the red line, right? And so I want to replicate that for every single point. And so the y hat would tell me where on the red line I am for any value of x. So I can do that manually. And so let me show you how to do that. So when I do this summary guy, you'll actually see over here that example.model1, when I did the summary of that, I was able to extract all this information in this nice little table thing. But actually, the example model contains a bunch of other information too. It actually contains the residuals, so that's like a punchline, you could just do that. But we're gonna first do it manually. And so if you do something like this, example model $1 coefficients, this will tell me the value of the coefficients, the intercept and the slope, right? So if I wanted to create a new variable in my for model.1, and by new variable I mean a new column, I'm gonna call this y hat. So that's going to be, we use the parameters that we have for the equation of a line. So that's going to be example.model1 coefficients, and I do square bracket 1, referring to the first entry value. So that's the intercept plus the slope, example.model1 coefficients 2. And what do I do with the slope? I multiply it against anyone? Yes, the x position. So that would be for model.1 $x. Okay? So that is going to give me y hat. And indeed, I'm just going to jump really quick. I know people are copying. So now I will have the position of on the line that corresponds to every x value, right? So all of these guys. And in fact, if I were to plot just the x and y hat, I have to do example dot, or no, for model $1 y hat. So if I plot this, those are all the points on the line, right? Does everyone follow along so far? Okay, great. And if I want the residuals, then we would do for model.1 $, I'm going to call it residuals. This is equal to our observed values, which is for model$1 $y, minus our predicted values, which is for model.1 $y hat. Okay? And I can plot the residuals by doing x is equal to for model$1 y hat compared to y equals for model.1 residuals. Great. Okay, so what do you guys think about these residuals here? Thumbs up or thumbs down? Thumbs up? Good, right? What are the features that we're looking for? We want this to be random, and we want it to be centered around 0. Both of which I think are generally true here, and so I would be, in this particular case, confident to say that we're not really observing biases in the model. Okay. This is the way that you would do it manually, but let me show you guys a couple of shortcuts. Okay, so shortcuts for y hat, i.e. the predicted values. So we did grab the coefficient plus grab the intercept plus grab the slope multiplied by the original values. Man, that would be really tedious if I had to do that for like 20 variables, right? So it turns out there's a function. Okay, so let me do this as a, maybe I won't even do it as a note. There's a function called predict. And if I just run this, so actually let me store this as y hat dot 2 as a new column in for model dot 1. Okay. Jump over here real quick, and you can see that we were able to generate the exact same thing using the predict function instead of doing it manually. Okay? So, a little bit of a shortcut. The predict function is essentially taking the original vector of x values And it can do it for multiple columns of X if you have a multiple regression. And plugging that into your model and getting your fit results. I could very easily ask it to predict a different set of values, in which case you would do something like this. So to predict new values, let's say I have a couple of points here. So example model 1, new data is equal to, let's just say, I think I have to have it as a data frame. Data frame X equals 25, 29, 42, 57. I believe that should work. Yeah. So then, in terms of points on the line, it would look like, if I plugged in 25 times the slope plus the intercept, it would be this. If I plugged in 29, it would be this, and this, and this, and so on. One small word of caution here, and this is something that we'll, touch on in other parts of the class. There might be something you should be a little bit hesitant about over here when I'm doing this predict. And does anyone see what that might be? And I'll give a hint. So I'm asking it to predict on these values. And here's our original draws. Yeah.
Because it goes above the.
Yeah, exactly. So in our original draws, we were drawing from a random distribution between 0 and 50. I have asked the model to predict what the line, where you should be on the line at a value of 57, which is like out of the bounds of where the model was kind of calibrated to. In this particular example, it's like, okay, it's obviously a line, and we know it's a line. But more principally, you should really think carefully about trying to do predictions, right, in places that you have no real data to kind of back up that initial calibration of the model. So yeah, generally we would be cautious about doing something like this, okay? So I'll just say, maybe I'll put here, caution about predicting values out of the original bounds. Okay. Shortcuts for residuals. So I'm going to do for model.1 dollar residuals 2. And there is a function where you can just do resid of the model object. And that'll just give you the residuals that correspond to the data points. So if I run this, we should see in this table, here's the residuals that we calculated manually, and here's the residuals that I just got from doing this resid function, and it's the same thing. Okay, So the first stuff is really just to iron out and make sure everyone really understands what's going on. I don't expect you to do that manually every time. You can just use the resid function. Okay. Okay, any questions about that? Okay. In that case, let me see here. Okay, let's continue onwards. One second. Okay, let's jump back over to the notes. Okay, so we've hit on one additional diagnostic tool. So we're adding right into our kind of tool belt ways that we can help judge the quality of a particular regression model. Right, so understanding the standard errors, the R squared, the residuals. What are some other things that we can think about? So I'm going to start with this one, the residual standard error. And this is just the standard deviation of residual values. Okay, this kind of what this describes is essentially what is the quote-unquote spread of points about the regression line. Okay, I'm going to write the equation, again, purely for your reference, not something you have to memorize, right? You can just use built-in functions to calculate this if needed. Residual square error. 1 over n minus 2 I equals 1 n of yi minus yi hat squared. So this is not one of the things that this particular metric it doesn't enjoy the same flexibility as something like an R squared, which is that an R squared is always or almost always between 0 and 1, and so the comparable nature of an R squared across many different models is really easy to compare. Whereas here, RSEs compare usually against the mean sort of value of y. And so it is kind of tethered specifically to the nature of the actual data itself. Nevertheless, this can be a useful metric, but it's not used that frequently in comparison to the next one that I'm going to talk about, which is very much similar to a residual standard error in many regards. And that is, and maybe some of you guys have heard of it, the mean square error. So the MSE. The average of the square of errors. So that looks pretty similar to the residual squared error. Okay, so we're going to spend a lot of time talking about the mean squared error. This is a metric that is heavily utilized across many different types of data analytic fields, and with pretty good reason. We're gonna kind of try and build our intuition on this in a moment. But particularly in, we talked about these diverging branches of regression data analysis, one that focuses on causal inferences and one that focuses on prediction. The mean squared error is probably the most used sort of metric in terms of predictive outcomes and being able to compare and contrast different models and their ability to best predict outcomes. The metric that measures that is very often the mean squared error. And all this is really doing is basically saying, okay, you have a model, you fit it to a bunch of data, and we have some errors associated with that. But it's a whole vector. It's a whole vector of these residuals, and so if I wanted to take all of that information about those residuals and sum it up all into one number, this would be the number that represents that, right? And so what do you compare with an MSE, right? That it is, again, like the RSE, not standardized in a way that it's between 0 and 1. It's closer to 1, it's better, right? You want your mean squared error to be kind of as small as possible, but the magnitude of the mean squared error really kind of depends on really the sort of original data. And so oftentimes the things that people compare against are when you are running models against the same response variable, the same y, then it becomes more of an apples of apples comparison to do what's the MSE of this model versus this model versus this model, because you're looking at the same sets of outcomes, okay? Okay, so let me jump to building our intuition for this. Okay, let's do this whole shenanigans again. Right, if I had a fit line that looks like this, versus something like this, versus something like this, versus something like this. Okay. Which of these lines, of these model fits, which color has the lowest, has the highest mean squared error? the blue, right? Every other line actually passes through every single point. And so technically the mean squared error of my red, green, and yellow lines are all 0, okay? And so that's, we're comparing apples to apples here because we're looking at the same data set, the same sort of outcomes. And so as far as being able to predict a particular value, we would actually say the red, green, and yellow all outperform the blue as it pertains to predicting those values. I don't remember if we kind of discussed this term in the very first class, but one of the things that jumps to people's mind is like, well, wait, this is like over prediction, right? And so what does that mean? Okay, and so mean squared error in this context is really helpful. And so let's actually think about that. So let's suppose that the x's in this that I'm showing in this plot are actually part of a larger data set, okay? And let's say that data set looks something like this. Oh, you know what? Actually, let me put in the original data points in first. Okay, so let's say these are the original data points. Okay, but those blue dots are a subset of a larger data set that is kind of like of the same nature. Okay, and so we have data that looks kind of like this. Okay. So suppose the original data is part of a larger data set. Now suddenly, let's just take the example of the red line, which is like this. Now, if I think about the mean squared error in the context of this new data, I'm suddenly doing a lot worse, right? Because now you've got all these, like for example, right here, I have a much more magnified error. Like anytime I'm in these like troughs and valleys, right?
So this kind of gives you a better idea of the model's predicted value.
Yeah, exactly. Compared to our original blue line that went like this, I can tell you with, a pretty good deal of certainty that the mean squared error of the original blue line with these new data points is going to be a lot better than this other thing. That's kind of, what we would describe as maybe sort of overfitting, right? And so you can think about how that might even be the mean squared error would be even more magnified in the green line example versus even the yellow line example, right? Because if my yellow line jumps all the way over here, the error here is 0, but the error for this guy is like huge, right? And so I think mean squared error kind of philosophically fills a really nice role when we think about intuitively what we want like predictive models to do, right? Which is I've built a model, and I think that model predicts outcomes based off of some kind of relationship that I've seen in data. And so how do I test how good that model is? Well, let's see how good it is at predicting, right? And so give it some new data points and see how it does. And that as kind of the ultimate factor of like saying how good a model is, that the MSE really represents an easy numeric sort of index to tell you the quality of those predictions, right? Especially if you're doing cross-model comparison. And yeah, we're gonna leverage the mean squared error in some ways to actually help improve models as well, right? Because you can think about like, I have a mean squared error for a model that I put in, and like let's figure out how we can like modify the model a little bit and point it in a direction that makes the MSE a slightly better. So, that is one of the ways that mean squared error is leveraged, and that we're going to show how to do that to get better and better predictions. Okay? Any questions about this? Confusions, comments? Yeah, I make fun of the standard error people and the R squared people who focus on that. I probably am probably too envious of the MSE in the same way. I think the MSE is like a way better indicator for quality of a model than the other things, yeah.
So what would you do if you can't get like the extra data to kind of like test this like this?
Well, we're going to talk about that. Okay. Yeah. So, very fundamentally, there is this idea that like the more data that you have, the better you can inform the model. And so I always want to be training my data on as much, or I want to be training my model on as much data as possible. But if I use up all the data, then I can never really test things that are out of that initial data set. And so there's this trade-off that we make on what we call testing and training data, where I take the full data set and I try and carve out a little bit of that data set to test with, but I retain enough that I'm still giving it enough to train well. And actually you can further do some techniques where I can do this iteratively in certain ways so that you actually, on average, train through everything but still retain testing data that you can use. So we're going to talk about some of those techniques later. But yeah, good question. And so this is the like concept of this procedure we're going to leverage a lot in this class. And I'll say that even in the real world applications, like MSE is really a gold standard for a lot of predictive outcomes. So there are speaking of like data where you have it for training and data that you use for testing, there were some like famous examples of like hackathons where like I think Netflix, there was a notable example where they would release all this data and in like these big hackathon events and see who could come up with the best like predictive model, and they would hold back all this testing data, and once everyone submitted their models, they would take those models, test them against this data set that they didn't have a chance to train on, and they would look at the predictive ability, and one of the metrics, one of the big metrics that they would focus on is who came up with models that would have the lowest mean squared error, right? And so, even in industry, even in like real world applications, like MSE really is kind of a really go-to standard for prediction. Yeah. All right. Okay, before I show how to implement that, which is actually not too complicated, let's do the one more final diagnostic device. I don't use this one too often. It's always in the like default settings, so I want to talk about it so that people understand what it means. And that is the F statistic. Whoa, my iPad is like blazing hot for some reason. Okay, so this is similar to a standard error. So the standard error, if you were thinking about it in like a purely statistics context, we think about these like hypotheses about what value should be, right? And so in a standard error, the hypothesis is that the coefficient is equal to 0, and then you're doing this like t-test against the value of the coefficient and the standard error to test the statistical probability that that's true or not. And so F statistic is doing basically the same thing, but the hypothesis is that all betas are equal to 0. What? Oh, interesting. It's just like the new Apple like notes thing that can solve equations. Okay, I just want to see what happens. Solve. No, nothing. All right. I guess I have not been replaced quite yet. Okay, so the interpretation of the F statistic is like very much, very similar to the interpretation of standard errors as it relates to a particular coefficient, where we say, oh, it's statistically significant at the 5% level or 10% level or whatever, that the value is different from 0, right? That's what we would say for the standard error interpretation. And the F statistic interpretation is like, it's statistically significant, and therefore it's unlikely that all of the coefficients are equal to 0. Okay, so it's basically the same thing where you're like lumping it all up. Okay, this is the equation for the F statistic, again, just for reference. Okay, and the only new term that you see here is the K, and K is representing each of your explanatory variables. So if you have like x1, x2, x3, your K would run from I equals 1 to 3. Okay.
Doesn't standard error compare against average?
It's the hypothesis of the standard error is that the mean value of your coefficient is equal to 0. Yeah. And this, the F statistic is saying that the mean value of all of the coefficients is equal to 0. Yeah.
Huh. I thought that was student T.
Huh?
I thought that was student T. Like,
So the t-test is in reference to the number of standard errors away from 0. So you're testing the hypothesis via that that test. Yeah. Okay, so this will be relevant for model selection later. So we don't really need to worry about it for now. But this is just so, you know, if you see the F statistic in the standard regression tables, this is what it means. Okay. Does anyone want me to clarify that more, or any questions about that? Okay. In which case, let us wrap up with more coding. Okay. So I can really quickly just show the F stat where that shows up. Summary, example, model 1. Okay, so we've seen all this before. Right, coefficients, standard error values, probabilities, and then right here at the bottom, we have the F statistic, which is 188.7 on 98 degrees of freedom. Degrees of freedom is equal to the number of data points in your sample minus the number of parameters that you are using to fit those data. So it would be 100 minus 2 because we have an intercept and one slope. Okay, and so you plug this into the test procedure, then this tells you the p-value is 2.2 e to the negative 16, which means it's very statistically significant, and therefore it's highly unlikely that the betas in totality should all be 0. Okay? And that just means that your model fit is probably doing something, basically. Okay, this also will tell you the residual standard error, but again, then your ability to interpret this is, you need a kind of a reference point, and that reference point is in comparison to other models. Okay, how would I calculate my mean squared error? What's the equation for mean squared error? This one I maybe do want you to memorize, but it's really not that hard. So who can tell me from your notes equation for mean squared error?
Variance divided by n. Variance divided by n.
Yeah, that's right. So variance divided by n, or variance is actually equal to, so if you look at the equation, y minus y hat squared, and then sum it all up. So what's y minus y hat? Residuals, right? So this is residuals squared, sum all of this divided by n. Okay? So if I wanted to calculate my mean squared error, pretty straightforward in this case. I can do for model.1 for model.1 dollar residuals, and I want to square this, and then I sum all of this up, and then I divide it by, what's n? Who can tell me? Yep. Yeah, count isn't real, well, it's not a thing in base R, but yeah. N row, yeah. So the number of data points is that's correct, and the way that we would get the number of data points is n row of our data set for model. Do that, and my MSE is 25.787. And so if I had other models that were operating on Y, I could compare the MSEs and see how they would perform. And then whichever one has the lowest one is the one that we are happiest with. Okay? Kind of. No testing set involved here yet, so that's why I'm caveating that. Yeah, so I think, okay, I know that there's some base function for calculating the MSE, but actually this one in particular might be handy to just kind of know, because the nature of how we're gonna play around with MSEs a lot in this class. We often are doing it in our own custom way. So yeah, just this one is probably one that would be good to know kind of off the top of your head. And it really is not that hard to type out and calculate. So okay. And that is how we calculate mean squared error. Does anyone have any questions about that? Yes.
Would it be the same to use like residual 2 instead of residual because they're exactly the same?
Yep. Residual 2 should do the exact same thing.
And in our assignments, do you expect us to use the resid, equate that function, or using the more manual method?
Oh, yeah. On all your assignments and projects, you do it however you want, right? It should be, this stuff. Me doing it manually is an attempt to help build the intuition and not to treat everything as a black box. And so I'm being purposely a little bit repetitive there, like writing it out and then writing it in code. But yeah, like the expectation for the class in doing the homeworks and the project is to try and learn to do things your own way in the way that you would actually do them if you're doing data analysis. So definitely feel free to take all the shortcuts that you want in the homeworks. That's totally fine, unless I'm like asking explicitly not to. Yeah.
So MSE is, I guess, applied to one variable at a time?
No, MSE. Remember that the residuals have already taken into account how all of the variables play into getting your outcome. And so you are further condensing a vector of residuals into one number, basically. So MSE is a single number diagnosis for the entire model.
Would give multiple outputs.
Yeah, still, right? So we do have multiple outputs, but we have one MSE. So to build the intuition again, where's my mouse? Let me be a little bit more explicit about what it is. An AB line. was it example model 1? Okay. All right. So the residuals is the distance from each point to the line, okay? And the mean squared error is you take all of those distances, square them, add them up, divide by the number of points, and you get a single number. And that tells you a kind of proxy information for like how large the errors are on average across everything. Make sense? It's like it's
Yeah.
essentially the average value of the error.
Calculating the residuals is, I guess, what reduces all of the
Yes,
variables down to just the
that's right.
value.
That's right. Yeah. So again to help visualize that a little bit, if you were to imagine that we had an x1 and x2, and that instead of points scattered on a paper, you have points scattered in space, and then instead of a line through all those points, you would have a plane going through all those points, right? And so now you're in multiple dimensions, it's getting harder to visualize, but if my plane is, if the plane going through all the points is this desk right here, and I have a point here, and I have a point here, the residual is still the distance of this point to the plane, right? And so that reduces all those dimensions to, again, a single vector of errors. So that's kind of the power of the residuals, is that it reduces the dimensionality of this diagnostic tool to just a vector of numbers. Yeah.
Is there a way that I can verify if the MSE that I calculated is right?
No. I
Do
mean,
I just trust it?
huh?
Do I just trust it?
Yeah, but I mean, it's kind of like, it's just another number amongst a lot of the diagnostic tools that we talk about, right? Well, we're not verifying any of these numbers, right? But they're just numbers. Or do you mean like, we calculated it manually, is what you mean? And then is there a built-in function to do MSE? Is that?
I'm not sure. I just.
Yeah, like if you were nervous that that you were doing it manually and that you calculated it wrong, yeah, I suppose you could try and use the built-in function, which probably is not going to be doing it wrong. Actually, does anyone know that MSE for a linear one off the top of your head? I don't actually. I'm like so used to constructing it manually that I actually don't know if there's a regular MSE function.
I looked it up when you were talking about it, but I think there's like a metrics package.
Oh, yeah. Okay, yeah, I remember that. Yeah, but you have to download a package, and yeah. I trust that you'll be able to calculate it correctly. Yeah. Okay, any other questions? Okay, I think we'll end a little bit early today. You guys get a bit of a break. Yeah.
I have questions about the
Yeah, sure. Yeah, if you guys have questions about the homework, and we got time, so I'm happy to help out with that.
Okay. I didn't quite get the RMD file.
Oh, the R Markdown.
Yeah.
Yeah, okay. Yeah, let me. So this is a template for R Markdown. When you say you didn't get, like, you don't understand what's going on.
Yeah.
Yeah. Okay. Okay. Give me 1 second. I think I got a tutorial at some point on some of this stuff.
I mean, I saw the tutorial in the website that you created.
Uh huh.
But yeah, I didn't really understand.
Yeah, okay, give me 1 second.
It kind of looks like another type of language, and I'm not sure if that's the case.
Oh, I think it saves to HTML, I need to convert that to PDF.
Yeah, sorry, let me find.
We can go directly to PDF.
So the idea, where's my, okay, sorry, let me, because I did have, okay, whatever, oh no, does this one actually compile? Because I didn't make this template, someone else did. So the kind of idea behind doing the R Markdown, this is kind of forced training for you guys. R Markdown is it is a standardized way of essentially producing like a document that acts kind of as a wrapper to any code that you're producing, you know, whether it be for homework or for a project or whatever use that you have for it. Because if I want to like turn the code into a document, you know, it could be pretty messy in terms of like what code is showing. And then, you know, there is what gets shown in the code versus what gets shown in the console. You know, that's hard to reconcile, right? And so the idea behind our Markdown is to create these like document templates that you can use to show that. And so the idea, so I can knit, which means to essentially put all the stuff together and produce the document. So this is how you would produce the output. So if I do knit to HTML, you can see, I think this will work. Please. Yes, okay. So in the template, it's kind of set up here, right? You have the header where you have information about, you know, the title, you know, the names and whatever, okay? So this is kind of what it would look like, but obviously you would fill it out, right? And the kind of cool thing about R Markdown, so you have to learn a little bit of the syntax to figure out how to like bold things and make titles and whatever. That I think is pretty manageable from like the tutorial. The main thing that you will be producing from this is that it can make text in like two main categories, right? So if I were just like to type out text as a Word document, you would have text like that, and you can have that text just be printed and not interpreted by R, right? Because if I just started typing sentences in R and you like passed it through the console, it would just go crazy, right? Like it would make all these errors because you're writing words that don't mean anything in the R language. So in R Markdown, I can actually write out stuff. But I can also I can take code and put it in there, and it can print out that code, and it'll actually print out results of that code. So let me show an example of that. And I'm gonna need help because I haven't done R Markdown in like 10 years. So, so everything in the triple quotes is when it's interpreting R, right? Who knows R Studio, or I mean R Markdown pretty well? Nobody. Yeah. Okay. So is what I'm saying correct? Is that yeah? Okay. So then outside of it, I can put text, right? I can say. Actually, where is the part where it's? Yeah. Okay, that's right. So I'm going to type some example text over here, and this text is just stuff that will show up in the document. Okay, and so if you do this, right, then it shows up here. Great. Okay, and then I can actually put in code. Yeah, so let's do this.
There's a template as well. Like it just lets you fill it in.
Yeah.
You go to like the top left. Very top left, that little plus sign all the way at the top.
Yeah.
To the left.
This one?
Like that, and then you go down to R Markdown,
R Markdown.
and then you can use template, or you can just start a new document.
Yep. Oh, yeah. And you're saying from here.
There's the GitHub one. There's the package vinegar, just like another example.
Yeah.
But you can also just start a new document.
Yeah. Just like up here.
Just hit OK. And
Yeah.
it'll open up a new environment for you.
Yeah, that's right. If you wanted to make a new one. I think the main thing that I want to show here is like just really quickly, like I can do this. If I set x is equal to 3 and y is equal to 2, you can see what happens here. This gets printed, right? But if you do z is equal to 4 when echo is false, I can knit this, and it won't show up. Okay, and then if I wanna show, a result or something, x plus y plus z, so see what happens. It'll print out the thing as well as the result of the operation. Okay, yeah.
I think in the assignment requirements, you said we should upload this as a PDF.
Yes.
Right? But
Oh.
for PDF, we need LaTeX, right?
Oh, yeah.
So can we also
Yes.
upload this in HTML?
Yeah. Let me change the assignment requirements to be okay with HTML. Lou, are you okay with that? People do HTML? Yeah, okay.
If you really want it in PDF,
You could save this as a PDF, yeah.
Oh.
Yeah. But yes, I think HTML or PDF is fine, yeah.
Also, if you do like that template, it gives you the option to do it as HTML, PDF, or a Word document.
Yeah, same here. So when you knit, actually,
But then for the knitting, I need a LaTeX to do it as a PDF.
yeah, you need a little bit of extra stuff to
I could download it. But
yeah, it's a little bit more of a hassle. So yeah, feel free to submit as an HTML. That's totally fine. Yeah. Sorry, I didn't properly prepare a tutorial here. I would definitely suggest that you guys look through the R tutorial that I put on the announcements, and if you still are having trouble, come talk to me or Lou. Yeah. Okay, thanks everyone.